Hi guys, and welcome to Lesson 11. Today we're going to talk about continuous distributions. So, suppose it's some drizzly Tuesday morning, and we want to guess how much rain is going to fall. Perhaps you'd say maybe half an inch of rain falls on a drizzly Tuesday morning. However, to be mathematically accurate, in mathematics we're completely precise. So when you say half an inch, we mean actually 0.5000000 on forever. So you're going to be wrong. In fact, even if the right answer was 0.500124729 and so on, your guess is actually wrong because it wasn't perfectly precise. Of course, this isn't how we talk in real life. When we say half an inch of rain, we mean half an inch plus or minus a little bit of rain, like maybe 4/10 to 6/10 of an inch or something. So for a discrete random variable, the probability of a particular value is positive. So if I flip a coin, the probability that I get 1 heads is 1/2, and the probability that I get 0 heads is also 1/2. So 1 and 0 have a positive probability. For a continuous random variable, the probability of getting a particular value is 0 for every particular value. So for example, the probability you get a phone call 1 hour from now is 0, because that 1 hour, mathematically, we mean 1.0000 and so on hours. That means you can't be off by even a fraction of a millisecond if you're going to say exactly 1 hour from now. So whenever we talk about this in a math class, when we say we're going to get about half an inch of rain, we need to talk about an actual interval. So maybe from like 0.5 to 0.6 inches of rain. That way there's a positive probability that the actual value lands in that interval. Likewise, we could talk about getting a phone call between 1 hour and 1 hour and 5 minutes from now. So to reemphasize, for a random variable, the probability you get a particular value x is 0 for all values x, just because it's too precise. And this is the difference between a continuous and a discrete random variable. So in a discrete random variable, the probability of getting a particular value is positive. And if we sum over all the positive possible outcomes, we get a probability of 1. Well, there's an analogous thing in the continuous case, but instead of summing over all possible outcomes, we integrate over all possible outcomes. And since the probability of each particular value is 0, we have to integrate from -infinity to infinity. So we don't rule out any of the outcomes in this, so we just integrate from -infinity to infinity of this function f of x, and f of x measures how likely x is going to be close to little x. So it's like if the next phone call is likely to be close to an hour, f of x might be large around the value of 1 hour. So if you remember from class, there's a function, a little p of x, called the p.m.f of our random variable. And p of x is the probability that the random variable is x. And that was the function that we were summing over on the last slide. And it represents how much of the mass is sitting on x. The p.d.f, or probability density function, is analogous to the p.m.f. So it roughly represents, or it represents the probability that the random variable is near x, in a sense. So that's the way to think about it. So let's suppose on that drizzly Tuesday morning, we think there maybe is like 1/2 to 0.6 inches of rain. And the actual rainfall is going to be between 0.3 inches and 1.5 inches, depending on how long it rains. What's the probability that we are correct? I should probably point out here that that's a pretty unrealistic distribution for rainfall. It probably isn't going to be equally likely between 0.3 and 1.5 inches. But that's actually not a question of probability, that's a question of statistics. We want to figure out what the distribution of some real-life phenomenon is. So assuming an equal value between 0.3 0.3 and 1.5 inches, the p.d.f is just a constant from 0.3 to 1.5, and it's 0 everywhere else. So whenever we take the integral, we know that 1, the total probability, has to be the integral from negative infinity to infinity of f of x dx, which will be the integral from 0.3 to 1.5 of some constant, because it's equally likely to be anywhere from 0.3 to 1.5. And we drop off the other parts of the real line on the integral because it's f is just 0 there. And that gives us 1.2 times that constant. And dividing over, we solve for the constant. We find that the constant is 5/6. Now we can use the constant to figure out the probability that our guess is correct. So our guess is between 0.5 and 0.6 inches. And therefore we must integrate the p.d.f over that interval. So we're going to integrate from 0.5 to 0.6, and f we just found was the constant 5/6. So we integrate 5/6 over that interval, and that gives us 1/12. So there's a 1/12 chance that our prediction is correct. The probability that's exactly 1/2 an inch, as we talked about, we can use the integral, but if you remember from calculus, taking the integral from a to a, or from a point to itself, it gives you 0 area. So if we take the integral from 0.5 to 0.5 of 5/6, we get 5/6 times 0, which is 0. So there's no area under the curve at one point. So just a warning, get ready to dust off your calculus books. We're about to start using integration quite a bit through this part of the course. So I'll see you guys in class.